Over the summer, I saw a video on YouTube showing dogs reacting to a 3D carpet with what appeared to be a hole in the middle. The dogs walked up to a carpet and either avoided it or jumped over it, even though they didn't know what it was. On the contrary, news media were reporting instances of self-driving cars crashing into telephone poles, large trucks, and other objects on the road. Currently, machine learning models use large amounts of data to train. Natural intelligence is the exact opposite. Humans and animals are able to learn with just a few examples. This causes artificial intelligence to make mistakes that seem trivial to humans. AI doesn't fully seem to mimic real intelligence. It can only follow rules which are learned from large amounts of data, but doesn't know why these rules exist. However, natural intelligence knows how to create these rules and uses common sense reasoning instead of a database. In this project, I wanted to understand what made artificial intelligence so different from natural intelligence, and we aim to understand and model dog behavior towards visual and auditory stimuli using machine learning. Some potential applications of this are helping to develop new AI technologies, for example, new robot dogs, and create new ways of working with dogs, such as creating training environments customized to a dog's natural reaction. Dog training can include training service dogs, military dogs, police dogs, rescue dogs, and companion dogs. And we hope that understanding animal intelligence could provide insight into understanding human intelligence. To do this, we record what a dog sees and hears from its own perspective, and use a machine learning model to learn the association between a dog's perceived visual and audio stimuli and the dog's reaction. I received help from my family dog, Ivy. I mounted a GoPro camera on her harness and collected video and audio recordings from Ivy's own egocentric perspective while walking her in neighborhood streets and parks, as well as recording her with an external camera. Here's a clip of what the GoPro camera captures. On the top right corner is what the external camera captures at the same time. After collecting video and audio recordings of her, I separated the videos into image frames and audio signals, which were aligned by time. The images were annotated with one of the 4 dog actions: sit, stand, walk, or smell. STFT was applied to the audio signals, producing a spectrogram, and motion fields, or motion information, was extracted from the image frames via template matching. The image frames, audio STFTs, and motion information was concatenated and fed into an extended convolutional neural network, or ECNN. In our experiments, the data was split into a training set, validation set, and testing set, with 70%, 10%, and 20% of the data in each respectively. The ECNN model structure is as follows. The image input, the image frames, went through 32 convolution filters of size 7x7, a batch normalization layer over color channels, and a max pooling layer with pool size 3x3. For the audio input STFTs, they went through batch normalization. And finally, for the motion input, they went through a max pooling layer with pool size 9x3. We trained the ECNN model over 40 hyperepochs and 4 hyperbatches. The performance on the validation set was used to select hyperparameters. We trained the ECNN model on single modal inputs as well, for example, image only, audio only, or motion only, to evaluate how single modal information is perceived by the dog. The overall prediction accuracy was 79.02%. We found that the use of hyperbatches achieves optimal performance and less number of epochs. Using 1 hyperbatch achieved optimal performance at around 20 hyperepochs, while using 4 hyperbatches achieved optimal performance at only 5 hyperepochs. Here are the convolutional filters learned by the model. We observe that the dog reacts to various color patterns and color contrasts. These are the graphs of the average weights on image inputs, audio inputs, and motion inputs. We found that the dog reacts strongly to some low-frequency components in what it hears. In this experiment, we proposed an ECNN model to learn and model the association between a dog's perceived visual and audio stimuli and the dog's behavior. The ECNN model showed promising results in predicting the dog's behavior, and we hope that the insights gained in this project could potentially create new ways of training service dogs for rescue work, companionship, and more. In the future, we plan to extend in the following directions. First, we want to add infrared sensors to study if and how dogs react to temperature. We also want to test sequence models such as recurrent neural networks for potential performance improvements. Third, we plan to extend data collection to study how a dog reacts to unfamiliar situations, human voices, other dogs barking, music, and much more. We also want to extend the study to different dogs and understand the general and individual behavior of dogs.